Okay, recording is on, so I will just start now. Let me turn my laptop, so I will switch up my camera now, and then I'll just start. I hope you can see my slide and I'm audible. So, okay, welcome to the NPTEL online um, classes problem solving session. The course is Coordination Chemistry, which is taken by Professor Devashish Ray from IIT Kharagpur, and I am Satyaprakash Yadav, a PMRF scholar from August 2020 batch 2 project. And I am working with Professor Satish Patil from SSU Department, Indian Institute of Science, Bangalore. So about the course, this is 12-week course. So in week one, we have I basically introduced to the coordination chemistry, and we solved based on the based on that we do the problems. Uh, we solved the problem. In week two, we have seen the nomenclature of cationic, anionic, and neutral complexes, and we have seen the nomenclature also where the cation and anion both were like complexes. In week 3, we see the coordination number from 3 to coordination number 12, what is their geometry and what are the critical points. In week number 4, we have discussed and we have solved the problem based on structure, symmetry isomerism, coordination equilibrium. So here, what are the different types of structural isomerism are possible and optical isomerism, and we have gone little bit in the coordination equilibrium. Okay, and then in week 5 we have went into the bonding in the complex. So this week I will do. So in the lecture number 14, professor has discussed about the coordination equilibrium 2, where he has just describing what are the different kind of what is the chelation, how and hard acid, how HSAB principle, hard soft acid base concept. And in lecture number 15, he has discussed the bonding in complexes. So basically, he has discussed about the valence bond theory. And in subsequent lecture also, he has discussed the valence bond theory. And in lecture number 16, he has discussed about the crystal field theory in detail. So in one, he has discussed the valence bond theory, two, valence bond, crystal field theory, and C, he has in 16, he has gone in detail in the crystal field theory. So before going to the assignment, I will just what I can do. I can introduce it. I will just introduce some new slide. Okay. So I will briefly discuss about the valence bond theory. So valence bond theory, which is known as VBT, valence bond theory is proposed by the Linus Pauling in 1931. So why it is called valence bond theory? Because here only valence orbital are used to explain the property of complexes. Okay, so first of all, why it is called the valence bond theory? Because here only valence orbital are used to explain the property of the complex. Now I will just go to the main points of VBT. Main points of VBT. So what are the main points of um, VBT? First thing is that this is the only theory which talks about geometry or shape of the complex. So here if we go to the what are the different kind of hybridization in shape, so just we can see if we have SP, then it is linear. We have SP2, it is triangular planar. If we have SP3, this is tetrahedral. If we have ST3 also, this is tetrahedral. If we have DSP2 or SP square T, these two are square planar. If we have DSP3 or SP3D, these are called the octahedral, and DSP3 or SP3, this is called square pyramidal. So okay, DSP3 is trigonal pyramidal, and this SP3D is square pyramidal. And DSP2, D2 SP3 or SP3 D2, these are the octahedral. So main point of VBT is, first point is that this is the only theory which talks about the geometry or shape of the complexes. Second point is that I will just take example of the octahedral complexes. So here what is this metal ions provides vacant orbital equal to the, very important, equal to the coordination number, or we can write the coordination number. How? Just by promoting the electron from one orbital to the other. Okay, now what we'll do, this vacant orbital hybridized to give the hybrid orbital. So suppose we have this octahedral complexes, so metal will provide the 6 vacant orbital, which will give the 6 equivalent hybrid orbital of D2sp3 or like that. So I will just take an example like FeCN6 4 minus. So we have like Fe here, Fe in 2 plus, so which is argon, first electric iron is argon, D6S2. Fe2 plus will be argon, D6. Now we have D6, so it's like this. one first 5 electron, then 6 electron will come. Now what will happen? And then we have this 4s and 4p. This is 3d. Now what will happen? Electron will just promote from one orbital to other orbital. Now Fe2 plus under the ligand environment. What will happen? Electron will just promote and now it will become 1, 2, 3. Now it has given the 6 vacant orbital, which is D2sp3. Now in this 6 orbital only coordinately Cn minus will come. 6 Cn minus ion will. Okay. So here this hybrid orbital will overlap. This suppose this metal hybrid orbital will overlap with the your Cn minus and give the complex. So important point is that note is that this hybridization is compulsory. Is compulsory for a particular shape. Okay, no hybridization means no shape. Okay, and third point is that it explain the magnetic property. Another thing is that they have not explained the region. There is no region why electrons are arranged. So suppose we will take one complex like Mn Cn6 4 minus. Now this is in manganese in plus 2. So first manganese is argon D5s2. So 3d5 4s2. So it is like d5. So now d5 we can write it like in the 1 2 3 5, each in one electron. Now it will rearrange. It will give like this 1 2 3. So it has one electron and this is the dsp2 d2 d2sp3 hybridization. So this is paramagnetic induction. So it is also known as magnetic criterion metal ligand bond or vice versa. So what if we know the magnetic moment, so we know that it is paramagnetic, so rearrange will happen. Other way is that if it is if we know the magnetic ligand, we can predict the metal ligand bond. If we know the metal ligand bond, we can prove the what is the magnetic moment like that. Okay, so he has explained. He has also explained the back bonding. This is, I will not go into the detail. Now I will just go to the what are the advantage of BBT and what are the other things I will discuss in the problems. So what are the so first advantage is that only theory to explain the geometry of complex. Second thing is that magnetic behavior of complexes, not in detail but to a certain extent. Third is that reactivity of the complex. to some extent. Okay, so these things we will come and we will do. Now, what are the limitations to balance bond theory? So it is just qualitative in nature, and that is no parameter for the comparing the stability reactivity. It can't explain the deviation of dipole moment, deviation of the dipole moment, like experimentally if we are measuring and theoretically. And it only explain the unpaired electron means paramagnetic, paired electron means diamond. It doesn't explain about the ferromagnetism and ferrimagnetism. It does not also explain the temperature dependent the magnetic property. It also does not explain the pairing of electron in presence of strong ligand pi. Like suppose if we have Fe F6 3 minus 4 minus, and we have Fe Cn6 4 minus. So here it is sp3d2, here it is d2sp3. Here this is diamagnetic and this is paramagnetic. So it does not explain like why the like pairing of electron happen under the strong field ligand and is not happening with the weak field ligand. Okay, so to explain these things, this crystal field theory came into the picture. So in crystal field theory, first it is given by 1929 by Van Arcle and Devor in 1922 to 1930. So what their main is that, so it considers interaction between metal ion and the ligand which is negatively charged. Metal is the positively charged, are purely electrostatic in nature. That is there the first. So if ligand are neutral, then we have ion dipole interaction. So they proposed, like if we have coordination number 6, that is octahedral. If coordination number 4, there is two types of tetrahedral and square planar. We will come into the detail. And first we have only this, and 2 we have linear. Okay, so what is their basis? So basically on the basis of minimum repulsion between metal and ligand, between the ligands they calculated the bond energy from the potential curve and matched with experimental value. Okay, so this is the way that theory has come out, and then there are different kind of scientists. Like in 1929, Bethe proposed the model of proposed the model, but Sculp and Penny in 1930 used this theory to explain the magnetochemistry of metal complexes. So if we go in the journey, so 1929, Bethe has proposed this model. In 1932, um, Sculp and Penny used this theory to explain the magnetochemistry. Then 1932 to 1950, basically Van Black used to explain the magnetic and electronic property. In 1951, then Leja and Cortman used to explain the color and spectra. And in 1952, this Argel, Jorgensen, Griffith, Nanman, and used to the different property like magnetism, magnetism, reactivity, and stability. Okay, so this is about the crystal field theory. So first, the important thing about the crystal field theory is that the electrostatic interaction. So it consider only the electrostatic interaction between between metal and ligand. And ligand are considered as point charge. Ligand are considered as point charge. Okay, so why this crystal field theory name? Why the crystal field theory name came? So because the interaction between metal and ligand is similar, why CFT name? So CFT is named due to the interaction between metal ion and ligand. Ligand is similar to that in the crystal. Okay, so it considered. Now they have something common, splitting in d orbital. d orbital. So we have to know that like dx y dyz dzx are the between the axis. Like suppose this is yx yz zx. So between the axis, this is dxy, this is dyz, this is dzx. Now the dz square and dx square minus y square are along the axis. Let me just introduce one. Just take. I will introduce one more slide. Okay, so suppose x square y square like along the axis. This is dx square minus y square, and dz square is like along the z direction. So this is z square. Now, if your suppose octahedral are like in all the direction x, y, z. In octahedral, ligand are coming along the along the all the six existential directions. So what will happen? Previously, in the in absence of ligand field, all the five d orbital are degenerate. But once ligand are coming along the axis direction, what will happen? Along the axis direction will destabilize and go into the up, and that uh, Between the axis one will stabilize and come down. So basically dxy, dyz, dzx. And dx square minus y square and dz square will be stable. And the between this is called delta or stabilizing energy. Stabilizing energy, or it's called crystal field splitting energy. Crystal field stabilizing energy or stabilizing energy. Okay. So in tetrahedral, what happens in tetrahedral? So in tetrahedral, ligand are approaching orbital between axis through an angle. So in tetrahedral, ligand approaches orbital between the angle between the axis through an angle more than more readily than along the axis. So in this, the ligand is approaching in between the axis through an angle. So what will happen? So first it is like in without it is all degenerate without once tetrahedral orbital spherically ligand will come, it will reach, and what will happen? The between the axis will go on up. This is called like dxy, dyz, dzx, and along the axis will stabilize dz square, dx square minus y square. So this is called E, and this is called T2. So this the name why it is coming like T2G and EG, and here it is T and T2. This is coming from the um, symmetry. Okay, once we discuss like that, then I will. And the tetrahedral, like crystal field splitting energy in tetrahedral is roughly half of the crystal field stabilization energy of octahedral. So E is like a tetrahedral. Now I will not go more into the detail. We will go to the problem solving session. So first question is, according to the valence bond theory, which kind of bond will form in the metal complexes? Coordinate bond, covalent bond, valence bond, and coordinate covalent bond. So we know that, like in valence band theory, that uh, the bond between the metal and ligand is coordinate covalent. Go to the question. What is geometry of COCl4 2 minus, and how many unpaired electrons are present in the complexes? So how we will solve it? So first we will write what is the cobalt. Okay. So what is cobalt? Cobalt is, it has Z atomic number is 27. So it is like Rn. After that 3d7 plus 4s2. So 18 plus 9. Now what is CO2 plus? So here coordination oxidation state of cobalt is 2. CO2 plus. So what is CO2 plus is argon 3d7 4s0. Now so I will just write CO2 plus. I will just make all the orbital. So we have 1, 2, 3, 4, 5. This is one rule, and then we'll pair 7. Now CO2 plus under the ligand environment. Ligand environment. Because Cl minus is weak field ligand, so no pairing will happen. So it will be like as such. 1, 2, 3, 4. Okay, we have this 3D, this is 4s, this is 4p. Now what will happen? So all these three 4 orbital will give a hybridization of sp3 hybridization where the Cl minus can bond. So once Cl minus can donate their orbital in this sp3 hybridization. This is okay. So we have hybridization sp3. How many unpaired electrons are there? 1, 2, 3. So 3 unpaired electrons. So the correct answer is the C, sp3 and 3. Among the complexes, which one is sp3 hybridized and diamagnetic in nature? Now I will just draw the so first here I will not write each and thing what is the metal. I will just directly draw the orbital. So nickel, here nickel 2 plus, here cobalt 2 plus, here nickel 2 plus, here zinc 2 plus. Now nickel 2 plus means D8. D8 means I will just write 1, 2, 3, 4 S P. So we have 1, 2, 3, 4, 5, 6, 7, 8. Now we have two unpaired electrons. Now it is strong field ligand. So what will happen? This will move here and now this is the structure. 1, 2, 3, 4. And this D2 SP D2 SP2 is the hybridization and this is diamagnetic. Yeah. But question is sp3 hybridized. So this is not correct. Now we have just seen the cobalt Cl4. So here we have the sp3 but there is 3 unpaired electron means this is not the this one diamagnetic in nature. Now we see NiClO4. So NiClO4 again 8 electron, 8 electron, 1, 2, 3, 6, 7. Now here we have, because under the Cl minus ligand, the pairing will not happen. So hybridization is sp3, but there is 2 unpaired electron. There is 2 unpaired electron. Unpaired electron. So this is also not. Now let's see the zinc. Zinc 2 plus is D10 configuration. D10 configuration means all are vital are filled. Okay, now we have yes, we have 3. So this is sp3 hybridized. There is no unpaired electron, means it's diamagnetic. So the correct answer is this. Now coming to the question number 4. According to which theory ligand are considered as point charge? So we know that in valence bond theory, valence orbital are used for the to explain the property of the complexes. Now, in crystal field theory, what we have considered that the interaction between metal and ligand are electrostatic in nature, and ligand are considered a point. So the correct answer is that C. Example of the soft acids are A. Silver, platinum, CH3Ac, B. Fe2 plus, Ag plus, Sn2 plus, Cr3 plus, Fe2 plus, CO3 plus, iodine plus, calcium 2 plus, and sodium. So first of all, where the soft acid concept has come. So first thing is that what is the HSAB principle? So here what says that like if we have a hard acid and hard base, this will give the most stable most stable compound. So and if we have soft acid and soft base, that will also give the most stable. So basically a hard acid prefer to combine with a hard base and a soft acid prefer to combine the soft Lewis base. Such combination give the more stable product. More stable product. Now, hard will be more ionic in nature and soft will be more covalent in nature. So the stability in soft is coming from the covalent and the stability from hard acid and hard base is coming from the ionic. Now, what is the property of hard acid in hard? So hard Lewis acid. What is hard Lewis acid? So basically, the first thing is that include first thing is that is smaller in size, smaller ions in size. So here the size will be small. Those consider the first and second alkali metal, and the D, basically from left side in higher oxidation state. Okay, so they are having the smaller size, have high positive charge. That is the second property. Third thing is coming from that they have high polarizing power. So these are the three property from the hard, hard Lewis acid. So what is the soft Lewis acid? So first thing is that they are larger in size. They have less polarizing power. So basically the metal in T block coming from the right side. So but in low oxidation state. So basically low oxidation state like silver plus. So if I give the example of hard, so we have, so first thing is that H plus, lithium plus. So all the M plus from the first, M2 plus from the second block element, and then we have the D block element in the left side, like in scandium 3 plus in higher oxidation state, titanium 4 plus, zirconium 4 plus, chromium 3 plus, like this. In soft acid, example are what are the example? Basically, D block element from right side in lower oxidation state, like palladium 2 plus, silver plus, and copper plus, and Hg2 plus, like this kind of metal. So what is the correct example? Correct example is this, like silver plus, platinum 2 plus, H3. These are the, now see Fe2 plus from left side coming, this is soft, but this is hard. This is hard, this is hard, this is hard. This is soft base, this is hard, this is hard. So the correct answer is this. Coming to this. According to HSL, which is not property of the hard acid and base. So hard acid and hard base, so they should be in higher oxidation state. Correct? Means it is asking this not, then high electronegativity, that is also correct. Low polarizability, and they have high polarizing power. These are also the property of the hard acid. So which is not the property of this is large ionic radius. They should be in smaller in size. Small ionic radius will be the property of the hard acid and base. Coming to the question number 7, which is following is correct? Homo of the soft bases are higher energy than hard bases. HUMO of the soft acid are higher energy than the hard uh, acid. HUMO of the soft bases are lower in energy. So first thing is that let me draw the expense. So I will write hard acid, hard base. We have to write soft acid, soft base. So what will happen there? This is the HOMO, this is the LUMO. This is the HOMO, this is the LUMO for the hard base. This is the HOMO and this is the LUMO. This is the HOMO for base and this is the LUMO. Okay, so here what is the combination? So HOMO of the soft bases, this is the HOMO, this is the LUMO. HOMO of soft bases are higher in energy than the hard bases. That is the correct answer. How? Because suppose we take the hard acid base. So now if we take it this, so this will be the overlap. Now here we have less covalent nature, but we have like A delta plus B delta minus. So they have higher ionic character, less covalent character. Here what will be having? We will be having like this. Here soft acid and soft base will give the larger covalent character since like suppose this is HA, this is HB, the electron are shared between these two, so it means less ionic character. So hard acid, hard base will give the ionic character. Soft bases and soft acid will give a more covalent character. So here we have less ion. So there, why this is happening? Because their homo are lower in energy than this soft bases, or you can say that homo are the soft bases have higher energy than hard bases. That's why we are having the more covalent character here and more ionic character here. Now we'll go to for the complex ion CuNH3 4 plus 2, the coordination geometry will be. What is the coordination geometry for the CuNH3 4 2 plus? So first thing is that I will write what is Cu. Cu use argon 3d9 4s2. Right? R because this valence cell will be not like this, it will be like 3d10 4s1. Why? We will know the like full filled and half filled. Half filled orbital like a fulfill and half fill concept is there. That's why this is more stable in energy than the less. So for like chromium will be 3d5 4s1 like this and this. So the first is 3d10 and 4s1. Then if we have like Cu2 plus, what it will be like? It will be like 3d9. So I will draw Cu9 2 plus 3 4 5 1 2 3 4 5 6 7 8 9, and then we have 4s and 4. Now in presence of NH3 ligand, what will be happening? It will be like same because there is no transfer of electron. Now what will happen? It will happen under the like if we have like Cu2 plus ion in CuNH3 4 2 plus, what will happen? It will be like 1 2 3 4. We have 2 to 4 6 7, and now we have this one. Okay, we have S, then it will take to P2 and then D. So this is Sp square D. Now the question is that why it is not going in the sp3 rather than going to dsp2. So this complex ion may be either tetrahedral or scarpolar, as both have one paired electron. But the physical measurement like diffraction, like XRT, EPR, EPR has one electron and indicate that it has the square planar geometry. Square planar geometry. So the thing is that like through the EPR and EPR and X-ray diffraction XRD studies suggest that the complex have square planar geometry. The Huggins says that it is SSP square D rather than DSP2, means this electron will move to the D. So that is not the like oh, like good answer. Huggins suggested that SP square D will be the better. So this is the square planar geometry and uh, square planar geometry mm, and it is paramagnetic in nature. This is the question number 9. Now question. Which of the following species is not in the paramagnetic in the nature? So paramagnetic in nature means it should have zero unpaired electron. So we have to see where we can find that zero unpaired electron. Now what is the uh, this I think Cl will not be there here. Okay, so we have this CuNH3. So we have to see that where it is paramagnetic. So this is Mn, it is D Mn3 plus. Mn3 plus means D4. This is weak field ligand, means all 4 electron will be there, so this is not there. NiClO4 we have already seen, it is a paramagnetic. Now the question is this. Now first is this is the Ag plus. Ag plus means it is Ag plus will come into the this one D copper family. So it is argon D10S1 because fulfill it should its rule is following fulfill. So Ag plus is D10. Under under the ligand field also it will be like in D10 configuration. So this is the correct answer. It is diamagnetic, not the paramagnetic. So it is like sp. So yes, and 1p will form a sp, and which is the linear in the geometry. Okay. In solution, if a compound absorbs red light, the solution will appear. So this is coming from the like a complementary color. So how we will find out this? So basically we will take the primary color, will generate the secondary color. So we have like 3 primary color. Okay, we have three primary color, 1, 2, 3. So in between we will generate the secondary color. Then we will generate the tertiary color here, 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 here. So this is called color wheel. Color wheel. So whatever the compound will absorb, the opposite color will be shown. So if it absorb the red, so the opposite color will be green. So people can go and look into the what is the color wheel, and I have just tell you how it forms. So first we will take the primary color. Primary color 3 color will be there. We generate 3 secondary color. Then in between 6 we will generate a tertiary color, and then find out like opposite color will, if observe this, the opposite color will be shown. Among the following complexes that is expected to show the highest magnetic moment at root temperature. Highest magnetic moment means highest magnetic moment means 1 minute. Okay. So highest moment magnetic moment means maximum maximum number of unpaired electron. Now we have to show that which complex has maximum number of unpaired electron. So first thing is that NiCNO4. NiCNO4 means D8. This is nickel in 2 plus complexes. D8 we can write. So we have 1, 2, 3, 4, 5, 6, 7, 8. Now this is strong field ligand, so pairing will happen. Okay, it will give 1, 2, 3, 4, 6. So it has zero magnetic moment because it has zero unpaired electron. Now come to the iron. Iron here it is in the 3 plus. So iron is D6S2 and it will give D5. Finally after the 3 plus. Okay. Okay. We have D5. Okay. It has D5. So D5 and it has a strong field ligand. So pairing will happen. So it will be like having one unpaired electron. So we will go to the CuH2O6. It is D9 configuration. So here we have also one unpaired electron. Now we will have here 3 plus. So this is D5. D5. So here it will be like 1, 2, 3, 4, 5. But Cn minus is a strong field again. Pairing will happen. Just give me 1 minute. Okay, so just give me 1 minute. Okay, this cobalt 3 plus is D6. Okay, D6 means all the 6 electron will be paired. Sorry, this one is there. And CuH2S6 is D9 configuration. It has also one paired electron. And FeCN6 3 minus. It has one unpaired electron. Now, which complex have the shows the highest magnetic moment at room temperature? Okay, so both are having one unpaired electron. So through this, we can't say that which one having the highest magnetic moment at room temperature. The if we see the actual value, FeCN6 3 minus is the correct answer. Now 13. NiCNO4 2 minus, NiCl4 2 minus complexes are. So we will just write NiCN4 minus. This is the D8. In a strong field ligand, it will be like first we will write 1, 2, 3, 4, 5. Okay, 6, 7, 8. Under a strong field ligand, pairing will happen and it will be like 2, 3, 4. So this is D8. Okay, so it is diamagnetic in nature. This is diamagnetic. NiCl4 2 minus. Now we have the 1 2 3 4 5. We have this is also we have D8, right? But this is the weak field ligand. So pairing will not happen. So it is paramagnetic in nature. So first one is diamagnetic, second is the paramagnetic. Now question is the number of molecules generated between the reaction of MH2O6 and EDTA. So the total number of molecule which generated from reaction of these two will be MEDTA plus 6 water molecule. So total will be the 7. So as we can see that here. So lead plus EDTA will form lead EDTA. So basically, okay. To take the eraser, right? Yeah, I can take the eraser. Okay, so basically we see that MEDTA plus 6 water molecule. So total number of molecule will be the 7. The product formed between the reaction of Fe3 plus and Au plus with NCS minus respectively. Now the thing is that Fe3 plus is hard acid. Gold plus is right side in low oxidation state. This is the soft acid. Now NCS has two sides. So if I ask, like if I tell you the basically NONX are hard bases. S bottom and iodide minus they are like soft bases. So now this is hard, it will prefer to bind with N. So we have to see that where iron bind with N. So if you see iron NCH3, so here it is bonding through N. These two might be the answer. Now gold is soft acid. It will bind through the S. So there are either it will be these two will be the characters. Well, gold SCN2 minus gold SCN2 minus. So this is the correct answer if we do the if we compare between ABC. Which of the following is not used in chelation therapy for arsenic poisoning? So, in arsenic poisoning, basically we use the uh, 1,2-dithiol. So, this is the main thing where we use the to bind the arsenic like chelation will happen with mercaptophtha. So what is dimercaptopropane sulfonate? So this is the dithiol. So if we write like okay, so this is like that. What I will just write. This is the SH. This is also SH, and this is the SO3H. This is dimercaptopropane sulfonate. So this is the uh, mm, this is correct. Dimercapriol because this has the sulfur which will bind the arsenic and form a chelate. Again is dimercapriol. So it is like this. SH, So here again we have this two sulfur to form a chelate ring with us. This we have dicarboxylic acid. So it is like this. We have SH, CO3, CO2H. Here also we have CO2H, and here we have SH. Okay, so here this SHSH is there. This can also bind, but only thing is that ethylene diamine tetraestic acid will not form a chelate with the arsenic poisoning. Second is in hard and soft combination of acid and bases. The suitable orbital uh, combination is. Now again we have to find out which is the suitable um, mm, uh, like a combination. So if we see that in hard, so I told you like low energy HOMO of base react with high energy of LUMO. Low energy of HOMO of base react with high energy of LUMO acid. This is the most important thing. Low energy HOMO of base react with high energy LUMO acid. That is the correct answer. The hybridization of metal atom and magnetic property of COCN6 minus COF6 minus R. So first thing is that here cobalt in plus 3. This is the strong field ligand and this is the weak field ligand. Okay. Now we have T6. Here also we have T6. So under the strong field ligand, so I will just write 1, 2, 3, 5. 1, 2, 3, 4, 5. 6. This is for weak field ligand. But for strong field ligand, what will happen? Pairing will happen 1, 2, 3, 6. So this is for the strong field ligand. So here D2 sp3 will form. Here what will form? Here S P 3p and later 2t. So here sp3d2. So the sp3d2 will be paramagnetic in nature and d2sp3 will be the diamagnetic in nature. So this is the d2sp3 diamagnetic outer uh, outer orbital octahedral complex, and this is called inner uh, this is called uh, inner orbital. This is called inner orbital octahedral complexes. This is called outer orbital. So which is the correct? COCN6. This is T2sp3 and diamagnetic. So this is the first is the correct answer. Now predict the structure and hybridization of metal ion in JTN OH 4 2 minus and NiCN 4 2 minus. So this is D10 big field ligand. So this is will be the sp3 and tetrahedral. Okay, this is D8 strong field ligand. So what will happen? Again, I will just draw the structure 1, 2, 3, 4, 5, 6, 7, 8. So it will be like DSP2 square planar. So D8 strong field ligand basically will be the square planar, and this will be the sp3 tetrahedral. So the correct option is D. Okay, which of the following statement is not correct in BBT approach? Okay, so if we see like bonding in complexes as a result of the electrostatic interaction, the theory is unable to do the inadequate explanation of magnetic property. It's correct. Cannot account the color of the complexes. That correct. All d orbital are actually in energy. That is the hybridization concept. The only thing is that this is the not correct. So the correct option is B. Okay, so which is not correct for PVT is bonding in complex a result of the electrostatic. So this is because crystal field. Which of the valence d orbital of the central metal ion in an octahedral ligand are raised in energy? So now we have like 5 degenerate d orbital under octahedral field, like it is coming along the axis. So what will happen? I told like first thing is that it will rise all 5 under the octahedral. Now what will happen? Further splitting will happen. The between the axis orbital like dxy, dyz, dzx will lower in energy, and dx square minus y square and dz square will be higher in energy. So the correct answer is B. The hybridization of what trigonal, pyramidal, and octahedral are. So trigonal pyramidal, I have already told what is the like answer. The answer is DSP3. D if you add with sp3. So we have sp3 like this and 1d will contribute on dz square orbital here. So dsp3, and this is the d2sp3 or sp3d2. Both are concept is possible. The correct answer is C. 1 mole of platinum PtCl4NH3 react with AgNO3 to give 3 mole of AgCl. The correct formula of that. This is again the Werner theory. Werner theory. So what Werner theory said that there are two kind of valency: primary valency and secondary. Primary valency is ionizable and non-directional in nature. Secondary valency is non-ionizable and directional in nature. So primary valency means ionic and non-directional. So suppose if we react with this with AgCl, 2 AgCl you will get. We react with this 1 AgCl you will get. Here if you react this 3 AgCl you will get. Here you will react no AgCl precipitation, because here we don't have any second. The correct option is C. Which of the following octahedral complexes is diamagnetic in nature? Again we have to see what are the like. This is Fe3 plus. Fe3 plus means D5. D5 means paramagnetic because anyway one electron paired. This is what? Fe3 is CO3. This is the D6 strong field ligand diamagnetic. NiH2O6 2 plus. So this is D8 weak field ligand paramagnetic. This is D6 weak field ligand paramagnetic. The correct answer is the CSUNH36. If you want in detail, just go into the detail little bit. Okay, how I will go? So this is iron CN6 3 minus. So iron is D6S2, 3 plus means D5. So iron 3 plus, right? Iron means D4. So D4 means first it will be like this 1 2 3 4, but due to strong field ligand pairing will happen and it will reach here. Final configuration will be like this 1 2. For this is CO3 plus. CO3 plus means D6 and it is strong field ligand. Sorry, this is D5. Strong field ligand, if will happen, then we have still one unpaired electron. Means this is the correct. No. Oh, it is. Which of the following octahedral complex is diamagnetic? Can we just see once again? Oh, okay. Sorry. This is D5. Right? D5 means it has one unpaired electron. Right? So it will be the paramagnetic in nature. Paramagnetic. This will be the D6 means diamagnetic in nature. That is the correct answer. And this is D8 strong field ligand means paramagnetic. This is D6 paramagnetic. On the basis of crystal field splitting theory, the electronic configuration for Fe6. So first thing is that iron 5, it will raise to 5 here. Then it has further 1 2 3. This is T2G, this is EG. Now iron 3 plus. Iron 3 plus means D6S2 means D5. D5 means 1 2 3 4 5. So we have T2G. Oh sorry, this is weak field ligand means it can go just 1 2 3 4 5 6. Sorry, this is 5 only, right? I will just write once again. Okay, weak field ligand means it can one electron it will fill in each. Okay, so this is T2G3 EG2. So that is the correct answer A. Okay, so that's it. Okay, so this is some like PPT I have already copied from professor's lectures, so you can go through all the thing I have explained. Okay, so let me stop the recording.